Okay, in this video, we'll look at several op-amp circuits which can do some basic math functions, which are foundations of analog electronics, or analog compute. In this video, we will look at several op-amp circuits to do some basic math functions which are foundations of analog computing. To do this, you need the following background. You need your knowledge from circuits 1 and 2, and all you need is KCL and KVL. 2, you need to know some basic rules about ideal op-amps. There are 2 rules. 1, there is no current going into the inverting or the non-inverting pin. And 2, there is a virtual short between the inverting and the non-inverting pin. That means the voltages at the inverting and non-inverting pin will always be equal, but there won't be any current flowing between them. So we will build all the circuits today using this basic knowledge. If you want to know why these 2 rules come about, watch this other video.
Cut.
The first circuit we'll be looking at is called the inverting amplifier. Okay, so this is a circuit. This is your input voltage Vi, and this is your output voltage Vo. The relationship between these two would be Vo over Vi, which is the gain, is equal to minus R2 over R1. So as you can see, if you can select your values for R2 and R1, and you can get any gain you want, but the gain will be negative. Okay, so now let's analyze the circuit. As we said, there is no current going through the non-inverting pin. Okay, that means the voltage at the non-inverting pin will be 0 because it is directly connected to ground now. Now, using the rule of virtual short, this means the voltage at the inverting pin is also 0. This means the current going through R1 is Vi over R1. Now, since there is no current going into the inverting pin, all this current should be going through R2. This means the voltage at the output Vo is given as 0, this is the voltage at the non-inverting pin, minus the drop on the resistor R2. You plug in the values and you get your result. Now, a note about R3. If this is an ideal op-amp, and we said it is, then there is no current going through R3, right? And we can select any arbitrary R3. But if this is not an ideal op-amp, then we have to select the value of R3 carefully. But we will look at that in later videos. Now, just to summarize, this is a circuit which is doing inverting amplification. The relationship between output and input is Vo over Vi is minus R2 over R1.
Cut.
All right, that was the inverting amplifier. Next, we'll be looking at non-inverting amplifier, which means positive gain. This is a circuit which does that. Now, again, the input is here, Vi, output is Vo. And the relationship between them in this circuit will be Vo over Vi will be equal to 1 plus R2 over R1. All right, now, how do we get that? The same rules apply again. There's no current going into the non-inverting pin, so the voltage at the non-inverting pin will be 0. Virtual short means the voltage at the inverting pin is also 0. Oh,
Cut.
okay. That was the inverting amplifier. Obviously, next we'll be looking at the non-inverting amplifier. This is a circuit which does that. Vi is the input, Vo is the output. Relationship between Vo and Vi is Vo over Vi is equal to 1 plus R2 over R1. Okay, let's analyze this circuit now. Okay, so the voltage Vi is being applied directly at the non-inverting pin. So the voltage at the non-inverting pin is Vi. Using virtual short, we can say that the voltage at the inverting pin is also Vi. This means the current going through R1 is Vi over R1. Okay. From this, we can apply a simple KVL and find the voltage at Vo using the voltage divider rule, or you can do simple KVL and you will get the answer. This is the derivation.
Cut.
All right, that was the inverting amplifier. Obviously, next we want to look at a non-inverting amplifier, which means can we get a positive gain? This is the circuit which does that. Okay, Vi is the input, Vo is the output. Relationship between Vo and Vi is Vo over Vi is equal to 1 plus R2 over R1. All right, now let's analyze this circuit. Vi is being applied directly at the non-inverting pin. So the voltage over there is Vi. So since there is a virtual short between the non-inverting and inverting pin, this means the voltage at the non-inverting pin is also Vi. Now this immediately implies that the voltage drop across R1 is Vi. Therefore, the current going through R1 is Vi over R1. Okay. Now, since there is no current coming out or in of the inverting pin, the entire current should be flowing through R2. This means the voltage at the output Vo is Vi plus the drop across R2. You plug in the values and you get the relationship.
Cut.
Good?
Yeah, I think that was pretty good tape.
Okay. All right. Now we have seen a positive gain and a negative gain. Now let's see how do we compute difference of two signals. Okay. Now this is a circuit which does that. The two inputs V1 and V2. The output is Vo. Relationship between them is Vo is R2 over R1 times V2 minus V1. So as you can see, the output is some constant times the difference of the signals, right? You can use, you can select your resistor values R2 and R1 and get any gain you want. This is a very common application where you want to compute the voltage difference between 2 points on a circuit. Okay, your oscilloscopes and any instrumentation. Okay.
Cut.
All right, we saw an inverting gain amplifier and a non-inverting gain amplifier. Obviously, the next thing we'll be looking at is how do we take a difference. Probably not that obvious. Okay, this is a circuit which does that. The two inputs, V1 and V2, and the output is Vo. Relationship between them, Vo is R2 over R1 times V2 minus V1. As you can see, this is just a constant times the difference of the signals. You can select your values for R1 and R2 and make any gain you want. Okay, let's analyze this circuit. Okay, now since there is no current going into the non-inverting pin, there is a voltage divider, and you can use a voltage divider rule. The voltage across R1 would be R1. Oh, cut.
Cut.
Okay, we have seen an inverting gain amplifier and a non-inverting gain amplifier. So next thing we'll be looking at is the difference between two signals. Okay, this is the circuit which does this. There are two inputs, V1 and V2, and there's one output, Vo. And the relationship between them is Vo is equal to R2 over R1 times V2 minus V1. Now, as you can see, the output is just a constant times the difference of the signals. You can select your values for R1 and R2 and make any gain you want. All right, let's analyze this circuit. Since there is no current going into the non-inverting pin, the resistors R1 and R2 on the top basically form a voltage divider. Okay, the total drop across R1 and R2 is V2. Therefore, the voltage drop across R2 would be R2 over R1 plus R2 times V2. Okay, let's call the voltage at the non-inverting pin V2 prime, and V2 prime is equal to what we just said. Now let's call the voltage at the inverting pin V1 prime. Okay, again, since there is no current going in or out of the inverting pin, the resistors R1 and R2 on the bottom also form a voltage divider. This means V1 prime will be equal to V1 plus the difference across the, damn.
Cut.
Let's call the voltage at the inverting pin V1 prime. Since there is no current coming in or out of the inverting pin, the resistors R1 and R2 on the bottom also form a voltage divider. This means the voltage V1 prime is equal to V1 plus the voltage drop across resistance R1, which is equal to R1 over R1 plus R2 times VO minus VI. Now, using the virtual short, you equate V1 prime to V2 prime. You shuffle things around and you get your relationship.
Cut.
Okay, let's analyze this circuit. Since there is no current going in or out of the non-inverting pin, the resistors R1 and R2 form a voltage divider on the top, right? So the total drop across R1 and R2 is V2. This means the voltage drop across R2 will be equal to R2 over R1 plus R2 times V2. Okay, and this will be the voltage at the non-inverting pin. Let's call that V2 prime. Now let's call the voltage at the inverting pin V1 prime. Now since there is no current going in or out of the inverting pin, the resistors R1 and R2 on the bottom also form a voltage divider. Okay, this means V1 prime is equal to V1 plus the voltage drop across R1. Since it's a voltage divider, this will be equal to V1 plus R1 over R1 plus R2 times VO minus V1, because VO minus V1 is the total voltage drop. Now, using the virtual short, we can say V2 prime will be equal to V1 prime. Shuffle things around and you get your result.
Cut.
Okay, so we saw positive amplification, negative amplification, and difference. Now let's see how do we do integration of voltages. Okay, now this is a circuit which does that. The first thing when I say integration, you probably thought about capacitors, right? And so obviously there is a capacitor in the circuit. The input is Vi of t and the output is Vo of t. The relationship between them is Vo of t is 1 over Rc times the integral of your input voltage. Okay, let's analyze this circuit. Same rules apply again. The voltage at the non-inverting pin is 0. Your virtual short, the voltage at the inverting pin is 0. Therefore, the current flowing through R1 is Vi of t over R1. Since there is no current going into the inverting pin, all that current will be going through the capacitor. Now, using KVL, the voltage Vo of t will be equal to 0 minus the voltage drop across the capacitor. All right. Now, how do you find the voltage drop across the capacitor? Let's look at this very simple circuit. There is a current I of t going into the capacitor, C, and let's say the voltage drop across the capacitor is Vc of t. Using our basic knowledge about how a capacitor works, the relationship between Vc of t and I of t is the capacitance C times derivative of the voltage across it. Okay, this means Vc of t is 1 over C times the integral of the current. You substitute this back in our equation and we get our result.
Cut.
Is that good?
4, 3.
Okay, let's analyze this circuit. Same rules apply again. Since there is no current going into the non-inverting pin, the voltage at the non-inverting pin is 0. Virtual short means the voltage at the inverting pin is also 0. This means the current going through R1 is Vi over R1. Again, since there is no current going into the inverting pin, all that current goes through the capacitor. Now, the voltage Vo is equal to 0, which is the voltage at the inverting pin, minus the voltage drop across the capacitor. Okay, now how do we compute the voltage drop across the capacitor? For that, let's look at this very simple circuit. There is a current I of t going into the capacitor C, and the voltage drop across the capacitor is Vc of t. Using our foundational knowledge about how capacitors work, I of t will be C times the derivative of the voltage drop across the capacitor. This means Vc of t is 1 over C times the integral of the current. You substitute this back into the equation we previously had, you get your result.
Cut. Cut.
At the end. Okay, let's analyze this circuit. The same rules apply again. Since there is no current going into the non-inverting pin, the voltage there is 0. Using virtual short, you can say the voltage at the inverting pin is also 0. This means the current going through R1 is Vi of t over R1. Now, since there is no current going into the inverting pin, all that current goes through the capacitor. Okay. Now, the output Vo of t is equal to 0, which is the voltage at the inverting pin, minus the voltage drop across the capacitor, Vc of t. Now, how do we compute Vc of t? Let's go back to our foundational knowledge about capacitors. If there is a current I of t going through the capacitor C, and the voltage drop across it is Vc of t, then we know I of t is C times the derivative of that voltage. This means the voltage Vc of t will be 1 over C times the integral of the current. You substitute this back in the equation and you get your result.
Cut.
Okay, since we saw integration, let's do differentiation. This is a circuit which does that. Vi is the input, Vo is the output. Let's analyze it. Same rules apply. No current going into the non-inverting pin, voltage over there is 0. Virtual short, voltage at the inverting pin is also 0. This means the voltage across the capacitor is Vi of t. The current going through the capacitor, I of t, will be equal to C times the derivative of Vi of t. Again, no current going into the inverting pin, so all that current is going to the resistor R1. The voltage Vo is 0, the voltage of the inverting pin, minus the voltage drop across R2, which is R2 times I of t. You substitute that in the equation and you get your result, which is Vo of t is minus Rc times the derivative of your input.
Cut.
Okay. Okay, let's summarize. So far we have seen positive amplification, negative amplification, difference of signals, integration, and differentiation. Now you can combine these to make lots of many different mathematical functions, right? So as we'll see in the future videos, we can do some variations of these to do very interesting applications.
Cut.
Okay, let's summarize now. In this video, we have seen circuits which can do positive amplification, negative amplification, difference of two signals, integration, and differentiation.
Cut.
Yeah, that's call. Okay, let's summarize. In this video, we have seen circuits which can do positive amplification, negative amplification, difference of two signals, integration, and differentiation. So these are building blocks of many complicated mathematical relationships. In the future videos, we will see how we can manipulate these basic building blocks and combine them to get quite complicated mathematical functions.
Cut.
Is that okay?